Bismillahirrahmanirrahim. Good morning. Today we will discuss the X-ray and the crystallography, how we can determine some important things in the crystal structure by using the X-ray. And we will explain what that means, XRD, and what the difference between XRD and the XRPD. That means XRD powder. What the important. What the benefit when you use this process like that, and many another important information related with this topic. Let's start from what is the XRD. XRD, that means X-ray diffraction. It is a non-destructive technique for analyzing the structure of materials. We will use the structure to determine some important things. For example, to know this structure, scopic structure or tetragonal structure, and many things like that. Primarily at the atomic and or molecular level. That's mean here by using this technique we can focus on two things, on the atomic and molecular, the both of them. XRD, that's mean X-ray diffraction. X-ray diffraction relies on the fact that X-rays are a form of light with wavelength of on the order of nanometers. That means X-ray is form of light with many different wavelengths on the order of nanometers. It is used to identify the crystalline phase present in a material. It will work on now. Let's know how we can use this process. We will go deeply with this important information. It will work on the size of the unit cell. This will be important condition. If the size of unit cell has a good size, we will deal with it by using XRD, X-ray diffraction. It's smaller than, we will use another technique. I will explain all of this information on the next slides. And the arrangement of atoms. That's mean here on this process we will depend on two conditions: the size of the unit cell and the arrangement of the atoms. And crystal determined from measurements of the diffraction of X-ray by crystal. Now let's ask, how can X-ray be used to determine the structure of solids? X-ray crystallography is a method of determining the arrangement of atoms. Like I said before, we will focus on the size of the atom and the arrangement of these atoms within any crystal, of atoms within any crystal, in which a beam of X-ray. Now we will know how this process do, how we can benefit from this phenomena. What is the phenomena here? In which a beam of X-rays strikes a crystal at the first moment from the incident beam of X-ray on the structure. What will happen? I will use another photo, another image to illustrate that very well, and scatters into many different directions. At the first moment, incident beam, and after that scatters from the another side into many different directions, like here, X-ray beam. After that, diffracted X-ray beam. What we'll do, we will discuss this next part of this image at the next slides. From the angles and intensities of these scattered beams, a 3D picture of the density of electrons within the crystal can be produced from this electron density. From what this 3D picture will produce, depending on the angles and the intensities of these scattered beam. Let's take another. Depend on the density of this scattered beam and the atom the angles and the intensities. The angles is different to all of these three beams, and the intensities of all of these, it's different here. That's clear. Let's say it's more than the other, on the left and the right, because these angles and different intensities of all of these beams, we will see image, something in this plate. I will explain the other at the next slides. The mean positions of the atoms in the crystal can be determined, as well as their chemical bonds, their disorder, and another information. All of these positions has a meaning to any atom in the crystal can be determined by these positions. By these pi positions, we can determine some qualities related by their chemical bonds and these disorders, and many another information. Since very many materials come from crystals, such as many collected with many materials, when collected with the other, can form crystals such as salts, metals, minerals, semiconductors, and various inorganic or organic and biological molecules. Note, X-ray crystallography has been fundamental in the development of many scientific fields, because that is important, not just to determine the kind of structure, but we can use it. Actually, we use it in many other fields. X-ray, why are X-rays used to investigate the structure of solids? Sure, we have a benefit. Why this topic to us is very interesting, because X-ray have wavelengths similar to the size of atoms. Let's be careful here, because these two qualities, these two properties, we can use it very well to investigate in the crystal structure, because X-rays have wavelengths similar to the size of atoms. That's mean they are useful to explore within crystals. Thus, since X-ray have a smaller wavelength than visible light, it's similar to the atoms, these X-ray wavelengths, but similar than the wavelength, the visible light. They have, what does mean? That's mean it has a higher energy than visible light. They have higher energy. With their higher energy, what will do? X-ray can penetrate matter more easily than a visible light. Why? Because it has a wavelength similar than the atoms. I'm talking about the size, and at the same time smaller than wavelengths at the visible light. What does mean? That's mean because all of these two properties, the X-ray energy, the X-ray property, how I can say, the X-ray properties will be better than the normal visible light, higher energy than visible light, because that we can use it to determine the crystal structure, because it has ability to penetrate the matter more than the visible light. How can X-ray diffraction method be used to study the structure of compound? Now here we're going deeply to the information. How can X-ray diffraction method be used to study the structure of a compound? Let's know how this process do. X-ray diffraction, or we can say XRD, X-ray diffraction, is used for phase analysis, crystalline variants, and to study the grain and particle size of the nanomaterials. We use it to three things: phase analysis, crystalline variants, and to study the grain and particle size of the nanomaterials. X-ray diffraction spectroscopy, what that's mean? It is as a rapid analysis technique is used to identify the type of materials. It is as a rapid analysis technique, faster analysis technique is used to identify, to know the type of materials as well as its phase, crystalline, and the last, the properties. We use this technique. It's a faster analysis technique used to know the type of material as its phase, crystalline, and properties. Phase, crystalline, properties. X-ray crystallography. Why do X-rays determine chemical structure? The incident X-ray beam is scattered by these electron densities and generates a diffraction pattern. That's mean why we have scattered beam. When we put directly this X-ray beam on the structure, crystallography structure, because two things. First one, electron densities, and generates diffraction patterns. Generates a diffraction patterns that can be used to determine the crystal structure of a given chemical. Which method used for determination of crystal structure? X-ray crystallography is the experimental science determining the atomic and molecular structure of this crystal. Like I said before, we focused on these two things, the atoms and the moleculars. One of them, in which the crystalline structure gazes a beam of incident X-rays to diffract into many specific directions. How do you determine the crystal structure of a metal? Metal crystal structure and specific metal properties are determined by metallic bonding, and force holding together at the atom of metals. At the metal, we focus on two things, or we can say the specific metal properties are determined by the metallic bonding and the forcing between or holding together the atoms of metal. Each of the atoms of the metal contributes its valence electron. It's important. Each of the atoms of the metal contributes its valence electrons to the crystal lattice, forming an electron cloud, or we can say electron cloud or gas, surrounding the position metal ions. The position metal ions will be at the middle. The electron cloud or gas will be around this position positive metal ions. These atoms of the metal will contribute the valence electron to the crystal lattice, because that we have an electron cloud, or we can say gas around the positively or positive metal ion. How does X-ray diffraction determine structure? I repeated that, but with some different solutions. By measuring the reciprocal lattice space. Lattice space is the lattice. This word is very important in all the solid course. I explained, I have a lecture. We was discussing about what is the lattice and what most of the important information related with this word. space K space by X-ray diffraction technique. If we take Fourier transform of that, it will give you a previous lattice. If we take Fourier transform of that, that means will give you, or we will take, or we will deal with previous lattice. This previous lattice will give us the information about crystal structure. Here, let's take a look. The first beam at the first atom, the second, the different angles. Okay, all these atoms. Here at the next slides, we will explain what that the Bragg's law and from where we have. It's very important. Bragg's law, 2d sine theta equal n lambda, 2d sine theta equal n lambda. And here we have different waves of wavelengths of lambda. How do you determine phase from X-ray diffraction data? The measured diffraction to peak positions, intensities. The measured diffraction to peak positions, intensities are like a fingerprint. That's mean here we will focus on the peak positions and intensities, because all of these will be something like printing to us to explain what we want. Fingerprint of a particular crystalline phase. To gain the crystalline phase position or information, we will dealing with peak positions and intensities. Identification is accomplished by comparison of the measured pattern with the entire in reference database using research match algorithm. This is also known as a qualitative phase analysis. Qualitative phase analysis is focus on the peak positions and intensities, because all of these will be something like printing to us or fingerprint to us of a particular crystalline phase. Identification is accomplished by a comparison of the measured pattern with the enters and reference database. Comparison of the measured pattern with the enters measured pattern and with the enters and reference database using a research search match algorithm. This is known a qualitative phase analysis. All of these words is a definition to qualitative phase analysis. The most important things in this slide and the qualitative phase analysis, or when determine the phase by using X-ray diffraction, we will focus on the peak positions and the intensities, because will be something like printing to us. When we focus on all of these, we will know the particular crystalline phase. And the important comparison between the measured pattern and the enters and the reference database by using the algorithm technique. Algorithm, the right pronunciation to this word is algorithm. Here is a great image actually. This the power, this the LED screen. We will focus from here to here. The most important area will be inside the square. Here, this beam, this the crystal structure, crystalline solid. Here we have a different of wavelengths with different density. because that we have these few points inside something like a circle. Here at the middle, spot from incident beam, spot from incident beam. Here at the area, at the orientation, at the last shell, we can say spot from diffracted, spots from diffracted X-ray. Here, spot from incident beam. Here, spot from diffracted X-ray. Here, at this point, like I think it will be stronger than the other, has bigger the wavelength than the other, because it came directly from the incident beam. Here, spots from diffracted X-rays, that means came from weaker wavelength. Here, this plate is a photographic plate. Okay, this the structure we can say. Because all of these points, we can say we dealing with this kind of crystalline. The phenomena by which X-rays are reflected from the atoms in a crystalline solid is called diffraction. XRD, X-ray diffraction, generate a pattern that reveals structure orientation of each atom in a given compound. X-ray diffraction is extensively used in chemistry for the characterization of organic and inorganic. And actually, let me say, this X-ray technique not just to determine the crystalline, the crystal structure, no, but we can use it to analyze the protein, the DNA, compounds that are made for pharmaceutical compounds, something like a medicines field, related with the medicines field, or making a batteries of the cell phones. Compounds that are made for the medical fields and making a batteries of the cell phones. X-ray diffraction technique is based on the elastic, the flexibility of scattering of X-ray. Why this technique is amazing to us? We're depending on what? We're depending on elastic, or we can say the flexibility, scattering of X-ray from structures that have long range order, have long range of crystalline solids, have long range. This X-ray have good two properties. The first one, because that we can deal it when we want to determine the structure of crystalline, the high elastic scattering in this beam, and the long range order in this kind of beam. X-ray diffraction technique is divided into two categories based on the morphology and the size of symbol. X-ray diffraction technique is divided into two categories based on the morphology and the size of symbol. Let's talk about the first one. If a crystal sample is large, actually we will focus on that. Like I said before, X-ray diffraction technique is divided into two categories based on what? The morphology, the first one. The two, the size. We will discuss number two, the size. When we have a large sample enough, when we have small sample, what the difference? How we can determine the structure, the crystalline structure to this sample by using what? How we will use it, how this process will be, what the different. Let's know all of this information. Let's go on. If a crystal sample is large enough, then it can be analyzed by using X-ray single crystal diffraction. When a crystal sample is large enough, then it can be analyzed by using X-ray diffraction, XRD. That's condition. Must the sample be large enough to can dealing with the X-ray diffraction. We solve for the complete structure ranging from simple inorganic solid to complex molecules. Note crystals of large enough size. That means they are still small enough for the normal eyes. Not that mean big, we can see it, no way. Most of the time, like a speck of dirt. This the bigger one will be like or belong to a bigger group, like a speck of dirt. X-ray diffraction is an important method to characterize the structure of the crystal material. Like I said before, it can be used to determine the lattice parameter and arrangement of individual atoms in a single crystal. It's important. Or the phase analysis in case of polycrystalline materials and compounds. It can be used to determine the lattice parameters, is important, arrangement of the individual atom, or we can say the phase analysis in the crystal, in the case of crystalline. The lattice parameter, arrangement of the atoms, or the phase analysis. Now, how we can deal with the small atom, how we can determine a small atom to know the crystal properties, crystal characteristics. Doesn't form crystals large enough. What we will do, what the technique we will do, if we will use the same technique or not, and if not, what the difference will be. Then the sample is analyzed by using X-ray powder with the small atoms, with the atoms not large enough, diffraction technique. Powder of crystalline material, diffracted X-rays, a beam of X-rays passing through a sample with randomly oriented microcrystals produces. What that means, that's important. Why here is very effect. The X-ray powder diffraction is a fact, as we can use it with higher benefit than the normal X-ray diffraction, because a beam of X-ray passing through a sample with a randomly oriented microcrystalline produce a pattern of rings on a distant screen. X-ray powder diffraction provides less information than X-ray singles crystalline diffraction. However, it's much simple and faster. Here is important because that we use it with the small atoms. It's simple and faster. It's useful for confirming the identity of solid material and determining the crystalline and phase purity. It's enough to us because we want to know the solid material kind, determining the crystallinity, and determine the phase purity, because that it's enough to us, and at the same time can deal with the small atoms by more simple method and faster at the same time than the X-ray diffraction. Let's take this a look. It's clear. It's better to us. Provides less information than, that's not important to us. It is much simple and faster than the X-ray here. X-ray diffraction, from the normal X-ray diffraction. It's useful for confirming the identity of a solid material. It's important. Determining the crystallinity, the phase purity. By simple method, by faster way, when it dealing with the small atom of crystal structure. What the principle of XRD, X-ray diffraction, finds the geometry or shape of molecular using X-ray. X-ray diffraction techniques are based on the elastic scattering, like I said before, of X-rays from structure that have long range order. The X-ray gate diffracted by a crystal. The X-ray, let me focus here, the X-ray gate diffracted by a crystal because the wavelength of X-ray is smaller to enter atoms spacing in the crystals. Like I said before, it's smaller and have more wavelengths because that has more energy, more active than the visible light, can pass to the material easier than the visible light and faster than. X-rays equal the inter-atom spacing in the crystal. Like I said before, the X-ray gets diffracted by a crystal because the wavelength of X-rays is smaller, similar to the atoms, and I'm talking about the crystal atoms and the crystal structure. Spacing in the crystals at the same time has different wavelengths from the visible light because that can enter easier than the visible light, like we explained on the previous lecture, the previous slides. When the X-ray beam encounters the regular 3D arrangements of the atom in a crystal, like I said at the plate, when we was dealing with some points, randomly points inside something like square, at the middle point, it was stronger than the last one because the different wavelength. The point it was came from the incident X-ray beam, but the other came from the diffracted X-ray beams. That's mean a weaker wavelength than the middle point. Most of the X-rays will destructively interfere with each other and cancel each other. Here is important. Here we're talking about another thing related with the plate figure or the plate imaginary image. Most the off X-ray. Here we will dealing with two groups with X-ray. Group number one will be stronger by support each other. Group number two will cancel each other. Let's go on with the information. Most of the X-rays will destructively interfere with each other. What does mean? That means we'll cancel each other because here we dealing with destructively phenomena. Destructively interfere with each other and cancel each other because here we have destructively process. But in some specific diffraction, the X-ray beams interfere constructively will support each other and reinforce one another. It is these reinforced diffracted X-rays that is used for crystalline structure determination. Here it's important, this law is important, this form. These reflections occur only under certain conditions which satisfy this equation. I repeat, that's important note. These reflections, talking about this, all of these reflections occur only under a certain conditions. What this condition? This condition is all of these reflection X-ray will be under this form condition, and lambda equal to d sine theta, because here I have theta and here is different. D is the distance between these 2 points, the first one and the second, or the same time, the same thing with the all 2 following atoms, the distance between 2 atoms. Here, this D. Theta, sine theta, we know it. And I will talk about it at the next slide. 2 wavelengths, 2 waves is in phase will have constructive interference of interference beams like that, of the difference in path lengths 2a, in difference in path lengths 2a is an integral number. N will be integral number, 2a will be a 2 integral number, that's mean 1, 2, something like that, of wavelengths. Let's take a look. And lambda will be 2a. Let's know from where this and lambda coming. And lambda equal to a. Okay. Sine theta what equal? Equal what? Sine theta equal a divided on d. Let's calculate the a result. A will be d sine theta here. Let's put instead of a here d sine theta to be n lambda equal to d sine theta. Like that, you can have the Bragg's law. Here is the Bragg's law. Bragg's law. We will use it in this field. Typically, the angle that produces constructively interference is measured, and the distance between atomic layers is calculated using d. D, like I said, between the distance between 2 atoms, following atoms, is collecting by using this form. From where this form? From the Bragg's law. D equal what? D equal N lambda divided on 2 sine theta. That's it. X-ray crystallography is used to determine the structure of simple atomic lattice and proteins. Like I said before, not just to crystalline structure, but we can use this technique to determine, to investigate the proteins and DNA and other biologically important molecules. Because like I said before, here this X-ray not just deal with the atoms, but we can deal with the molecules. The spacing between layers of here is example, simple example. Let's use the Bragg's law. Let's use Bragg's law by dealing with simple example. Let's use Bragg's law, the spacing between layers. What does mean? That's mean D of molybdenum atoms is 157 pm. PM that's mean picometer. Okay, pico like I think equal 10 to force minus 12. Like here, pico, yes. 10 to force minus 12. Let's keep going. Calculate the angle theta at here. The earth wanted from us theta, not sine theta. Okay, at which 154 pm picometer X-rays. It's the wavelength. That's mean it's lambda. Produce a maximum reflection for n equal 1. D equal n lambda divided on sine theta. D equal 157, lambda 154. Because the Bragg's law, n lambda equal 2d sine theta. What does mean? That means sine theta equal what? Sine theta will be equal n lambda divided on 2d to be like that. And after that, inverse sine to be theta equal approximately 30. Bragg's law Now let's discuss about the n. Here, the above equation is also known as, like I said before, n equal integer number 1, 2, doesn't matter. Lambda is the wavelength, d is the distance between the atomic lengths, like I said before. Theta is the angle of incidence of the X-rays beam. Incidence, that's mean from this side. Note, I didn't talk about the reflections. This path length difference must equal an integer value of the one of the incident X-rays beams for the constructive interference to occur such that a reinforced diffracted beam is produced. Here, that's it. Our lecture is done. It's something like summary about the most important information about all of these of this lecture. Thank you about your watching or listening. I wish it was helpful. See you in the next lecture.